Good time of the day, everyone, and happy 2026 to all of you. Welcome back to our series of online technology meetings provided by you by EPIC. And today we're discussing an exciting topic of photonics for hyperscale data centers. Let me remind you that EPIC, that provides you with this meeting, is the European Photonic Industry Consortium, the largest consortium of photonic companies in the world, comprising over 800 corporate members centered in Europe, but also all around the world. And EPIC is there to support you with technology expertise, with providing market reports, with opportunities in networking and accessing to new markets. It also provides you with mentorship support, HR support, and investment. So please don't hesitate to contact us if any of these services is of interest to you, and join our largest club of photonic industry companies in the world. So EPIC, apart from everything, also organizes many different events, and we'll be happy to have you with us in those events that take place also offline. So the coming few events will take place in San Francisco, aligned with Photonics West. There we'll have several receptions, and also in the EU Project and Pilot Lines Innovation Hub breakfast. So don't miss the opportunity to see us in person, and also come to our booth 15200. So apart from those events, we will continue also online meetings. So on photonics for cultural heritage, on expanding the talent pool, on measuring sustainability actions, on specialty optical fibers, and on defense. These are the upcoming meetings online and offline. For technology, we have a very exciting meeting for integrated photonics and packaging at PICs. I'd really like to highlight this meeting. It will take place on the 24th, 25th of February in Enschede in Netherlands. And we will gather the whole value chain of people working with integrated photonics, and especially packaging integrated photonics. So don't miss this opportunity, and sign up already now. Well, now coming back to our online meeting today. So photonics for hyperscale data centers. I mean, the topic could not be hotter than this. And we have a very hot lineup of speakers today also. We'll hear today from Lumentum, from Cascade, from Ipronics, Focuslight, from Chilas BV, from VPI Photonics, and also from Enica Partners. So 7 speakers altogether. We have 2 hours to share the ideas, to share the vision of this topic, and to hear about their latest developments in the industry. And yeah, without further delay, I will also first highlight that we have a very large audience today. Over 100 people are registered, and you can see they come from every level of supply chain in this topic. So we have a lot of end users and integrators here. This is a very R&D heavy topic, so of course a lot of R&D and universities, many components and modules providers, service providers, foundries, equipment manufacturers, materials. So all of these people are with us in the room. So please feel free to use the chat of this meeting also to get connected. If any of them also is of interest to you, don't hesitate to contact me, and I'll be happy to put you in contact with them. That's the spirit of EPIC. And yeah, and I'm sure we'll have a lot to discuss after we hear the talks of our speakers today. Also to mention, this event is sponsored by PICs, the same company PICs that will host our meeting in the end of February. So PICs is a packaging house in the Netherlands, and they specialize in the high mix, low volume products of integrated photonics. So without further delay, I'd like to start our meeting, and I'm happy to present our first speaker that will do the keynote of this meeting, Christian Uricaret. He's a Senior Director for Product and Strategic Marketing at Lumentum. Hello, Christian.
Good afternoon,
And
or good morning, wherever you are.
Christian will talk about optical connectivity for hyperscale AI, why indium phosphide, CPO, and optical switching converge. Is that right?
That's correct.
All right, Christian, then the floor is yours. So
perfect.
Please
Thank you.
Go ahead, share your slides, and we're all ears.
Thank you, Ivan. I appreciate it. Let me make sure the right screen. Can you see my slides okay?
Yeah, you're good to go.
Perfect. Fantastic. Thank you. Good afternoon, good morning, everybody, wherever you are. Thank you for the opportunity, Ivan and team, for presenting at this forum. As Ivan mentioned, my name is Christian Ricariet. I'm Senior Director of Product and Strategic Marketing at Lumentum, based in San Jose. I've been with the company less than a year. Prior to that, I spent over 20 years at Finisar, now Coherent, and then for about 3.5 years at the Intel Silicon Photonics team. So the topic I'm going to talk about today is the conversions of three fundamental technologies, if you will, or emerging technologies that are critical to sustain and to enable the new requirements, the new needs of the data center, specifically for AI applications. And as you will see, and it says in the title of my talk in the agenda, they're actually indium phosphide photonics, they're co-packaged optics with external laser sources, and also optical circuit switching. And I'm going to try to articulate why we think those technologies are critical for the deployment of this new class of data centers. So some version of this slide has been shared by a lot of people in the industry, but this is my take of what it looks like. We all know that the AI workloads that are exploding in the size and complexity and amount of resources required, they have very different traffic patterns from a traditional front-end cloud data center network. The features of those workloads means that the GPU traffic is very heavy, is constant, is continuous, is not bursty. Is east-west primarily, obviously. It is also very, very latency sensitive. So any kind of burst errors cannot be easily repaired or counteracted. So all those training sessions needs to be restarted. So there's a lot of specific features around the traffic, around the nature of the traffic, that create a lot of stress in different points in the data center, in what is called now the back-end data center. And that accounts for the scale-out network, which is also a part of the back-end, which is the interconnectivity of the different GPU nodes, and also the scale-up network, which is the interconnection of the GPUs within a specific node. And that's an area of the network, the scale-up network, that is also growing tremendously and expected to grow even more. And it brings its own set of challenges that I will address as well. Namely, how do we connect those large amounts of GPUs, tens of thousands, approaching hundreds of thousands in many cases, with a connectivity that maintains memory coherency, for example, and that actually allows a synchronization between the different GPUs within a specific node. So that, again, brings its own set of challenges to the connectivity, to the networking piece in the data center, and that's what we are trying to address to different technologies. Again, so in summary, if you will, the three main challenges are shown there at the top right in our view. It is energy efficiency plus reach, which means, again, power consumption per delivered bit for the required reaches, right, that we have within both the scale up and the scale out. It is bandwidth density at the electrical interfaces, which means, how much I/O can I get from the GPU, from the GPU package, or whatever other, TPU or network switch in many cases. I'm sorry about that. And the third one is topology efficiency across the fabric. How do we make sure that the fabric supports the low latency low power requirements, given the huge increase in the size of these data centers? How do we decrease the total power for better sustainability? And also, again, how do we ensure that that latency is kept to a minimum to interconnect all these nodes? So again, topology efficiency at the fabric level is also very, very important. So a quick reminder at Lumentum, why we think we can execute at scale. We are a company that, for those of you that don't remember, we came out of JDS Uniphase 10 years ago, actually 11 years ago. In 2015 was when JDSU split into Lumentum from the optical component piece and Viavi Solutions for the test equipment part. So that's where we come from. That's our legacy. A lot of the teams and the fundamental technologies obviously are still there. From the old JDSU days, we have fundamental expertise in materials and devices, wafer level expertise and technologies developed over 20 years. LCOS, MEMS, WSS, you name it. Also at the product level, through multiple iterations of products. So that's why we believe that we're leveraging all these technologies and know-how through this couple of decades, 30 years, I believe, or more of the JDSU legacy into this new world of AI. So what are the three pillars that we are going to talk about today, where we're focusing the innovation for the AI data center? One is scalable light and modulation, right? How do we get more light faster, more efficiently? And that's basically using our indium phosphide platform, which is highly mature, has shipped many millions of devices very reliably. How do we now go into the next level of speed? How do we get to 400G and per lane and support that growth in a very efficient modulation as well? So that's one. The second one, as I mentioned, is fabric level efficiency, and that's where optical circuit switching comes into place to provide that level of performance and optimization of the network. And the third one is increasing the bandwidth density at the package boundary, and that's where CPO comes into play. And CPO, of course, a lot has been said, many different approaches, different technologies. We are early on at the moment participating through our ELS modules that I'm going to talk about as well, and why we think those are important certainly for the deployments, efficient deployments of CPO within these networks, and all the challenges that losing the pluggability at the optical engine level will bring. And we think many of those are mitigated by using this external laser source modules. Again, I'm not going to focus specifically on products, but more on system level perspective on the advantages that all of these technologies bring into play. So the first one is our indium phosphide technology and components. As I mentioned, Lumentum has a very long history of deployment, reliable deployment. Today we're deploying, and we've shipped and manufactured many millions of 100G and 200G per lane devices. We're now working on improving optically, obviously, those designs to support 400G per lane. What matters, as we know, in the hyperscale volumes is power efficiency, watts per gigabit per second, transmitter reliability, and manufacturability. So we're optimizing those three parameters to make sure that we can support the industry with this technology when it needs it. We believe indium phosphide will continue to play a very central role. It really has shown the ability to excel in various types of implementations of the material system, be it EMLs, obviously integrating the modulator, also providing very stable, low noise CW laser light sources for silicon photonic modules, for example, and it has proven that it can do that reliably at lower rates, and we think it will do so as well at 400G. So laser will continue to define system performance, and we expect to be we're working diligently to make sure that is ready when the industry needs it. We had a couple of demos earlier this year at OFC 2025. both with an EML operating at 448 gigabit per second, as well as a DFB with a Mach-Zehnder modulator integrated that we've also displayed on the show floor. So again, that's the first pillar, indium phosphide components and its evolution. The second one is optical switching, where it's all about, different angles of optical switching where we think will be optimized for this kind of applications. We've chosen MEMS technology for our optical circuit switch. As many of you know or remember, we have a long history both with MEMS and also with liquid crystal. We've deployed them extensively in our WSS product line through a couple of decades. And we've chosen MEMS specifically given specific performance parameters and ways to optimize the architecture and the performance of the device. We believe MEMS provides the best solution of the two, some of which I will mention in a second. The example shown here is our 300 by 300 port device. We've also have released a 64 port version for different applications. The first one will be spine switch replacement, network redundancy, or failover in our view. That's where you get the best bang for the buck, if you will. We also see other applications within the AI data center networks, specifically for scale-up with lower port switches, and also for scale across. Increasingly interested in looking at optical switching to optimize the networks there. Again, much has been said in the industry, but we're going to re-emphasize the benefits, right, of optical switching. We have now a switching device that has significantly lower power than your traditional electrical packet switching. It has ultra low latency, given that there is no O to E to O conversion, no packet processing required. This is switching across in the order of very quickly, milliseconds. It's actually switched into the other ports. There is a significant amount of savings in power. Our studies of 100,000 GPU deployments show a savings of around 65 to 70%, as I mentioned, with ultra low latency and with protocol independence. So given that there is no packetization or conversion to electrical, all of these devices in optical switching are protocol independent. They're also transparent across the multiple bands, so O band, C band, L band. Once you deploy an optical circuit switch in the data center networks, those are very future-proof for future upgrades into the network, being to a different band or to a different set of protocols. So again, we believe optical switching provides this very high level of optimization of those traffic flows. Complementing packet switching obviously will not fully replace it. So at certain points in the networks where the benefits are maximized, we believe that this is a very highly optimized solution. And obviously hyperscalers are looking at it. Obviously, one notable one has deployed optical circuit switch in their network already. And we think this will continue to happen in the network. Again, given the many different advantages that optical switching brings to complement packet switching in this kinds of requirements. Very quickly, we've shared this before. Our level of performance of our MEMS-based optical circuit switching, low insertion loss, typically around 1.5 dB, return loss of higher than 58 dB. Again, ultra wideband capability. That's what I think makes it interesting. Using MEMS means that we are fully able to transmit any of the bands, O, C, or L band, without any kind of changes into the device or any kind of replacements into the device. So the third one is CPO and its enabler in external laser sources. As many know, I hope in this audience, CPO directly addresses the increase in bandwidth density requirement, which means that compared to a pluggable transceiver, it can achieve much higher levels of picojoules per bit per millimeter. It can also do so at a longer reach than copper connectivity, and this is where the key factor is. Copper can support very high levels of bandwidth density, but however, it can go do so only a few meters. And with the increase in the size of GPU clusters and the amount of GPUs that have to be interconnected, interconnecting them within a single rack is no longer sufficient. People have to go outside the rack. Hyperscalers have multiple rack clusters of GPUs within the same cluster. And that's where you need optics. And you need optics with the right bandwidth density, with the right energy efficiency, with the right shoreline density at the package level. And that can be done only with CPO. We are participating, or we are enabling the industry with our external laser source module. At the moment, we are packaging our ultra high power laser as in an ELSFP form factor that we are offering, and we believe this is a very highly optimized solution in ensuring the deployment of these early systems, where people will go away from pluggable optics. They need a way to do serviceability, to support changing modules in case they fail, to support growth within a single host. So this pluggability at the light source module is a critical component. I would think it's very, very important. Obviously, using an ELS means removing the heat source of the lasers away from the optical engine, and that has very significant advantages in reducing the thermal management complexities at the host level. So that's obviously the primary advantage of using an external laser source. Pluggability is very nice, and then also resource sharing, right? These modules, these lasers, the ultra high power lasers have enough power to support multiple optical engines. So you can support many of them with a single module. So you save, again, thermal complexity, you save cost, you save real estate within the host by having a high power laser such as Lumentum's in those ELS modules or ELSFPs. I'm not going to dwell on this slide. I think many of us have already seen the announcement last year from GTC, also some of the recent announcements further on the silicon photonics plan for NVIDIA from CES earlier this week. So we're part of that ecosystem, as it was announced last year, where we're enabling that platform with our ultra high power lasers, which we package in a particular way for them. So we're part of that ecosystem. And again, this is the first early example, but hopefully, and we know that many more will come in the industry where CPO will start being deployed in the hopefully near future. So the last slide is more of a general slide, and means our view that this technology innovation is critical for scaling AI, and we don't see this cycle stopping anytime soon. Language models continue to increase in size and in complexity. We're in the early stages of deployment of AI, of using AI. Enterprise AI is only beginning to point its head. Many early applications. Somebody was asking the other day. I would compare this, the state of AI deployment and use today to what the internet was in the 90s, maybe, right? Late 90s, where everything was emerging, and we were looking for applications and way to more efficiently grow. And I think this growth will become much faster than what happened with the internet, even faster. And we need to be ready with technical innovation to support the levels of power and cost efficiency required across the network. This is, network level or infrastructure level cost in power, in sustainability, etc., to support even larger models, which in turn will require more hardware, right? So that cycle we don't see ending anytime soon. And again, we believe the three pillars are fundamental. Indium phosphide will continue to be highly relevant. Optical circuit switching increasingly relevant and important across the network, not only in the scale out. and then obviously CPO together with external laser sources, which will become, we believe, will continue to be the way to deploy that for the foreseeable future. With that, I thank you for your attention, and I'm not sure how much time we have left if you have any questions, but thank you for your time.
No, it's perfect timing, and thank you, Christian. A very exciting presentation. Nice.
Thank you.
Yeah, nice opening presentation, and I'm sure everybody got some interesting takeaway messages from this. So let me tell the audience that so after each presentation we have a Q&A session. So please feel free to push this raise hand button at the bottom of your Zoom screen, and I pass you the word if you have a question for a speaker. I'll just start myself with asking Christian. So yeah, I mean, congratulations with this nice achievements of the 400 gig per lane in your product. However, so when do you think this will actually, dominate the market, the 400 gig per lane type of transceivers, and especially in the view of this, infinite cycle that you've just shown on the last slide. So how soon is this becoming real? And also, is there something that our, the members of our community can support Lumentum with in, in these developments?
Yeah, so that's a good question. So obviously it's a very complex problem, and many people are working on the 400G ecosystem at different levels. It's this innovation, this evolution of one lane to the other is becoming less and less linear or simple, obviously, as the decades, 25 years in the industry. There are people looking out there, looking for other solutions, interim solutions, ways to grow in maybe in a more brute force way, still using 200G. I think we'll see a combination of solutions and implementations in the near future. It's hard to set a timeline. I mean, I'm not in any way disclosing any kind of product roadmap, but in my own personal view, I think 400G will start to be deployed maybe in maybe a couple of years in volume. I think it will take us another year or two to iron out all the details and make it very efficient, a way to manufacture efficiently and in very high volume. So I think will happen maybe towards the end of next year. It's my own personal view.
Nice. Okay, that's an interesting projection. So anything that our EPIC members could support you with in this regards?
Well, nothing comes to mind specifically. Obviously, many of the companies here, I think, are engaged with us at many different levels. We have a very broad base of products and technologies. Continue to support us. We really love working with the ecosystem. No company can do it alone, and we're excited about the growth that's ahead of us. We've shown it in the last year, and we continue to believe that it will grow even faster. And so, if you're engaged with us, please continue to do so. We're very happy to work with everyone.
Okay, perfect. Thanks a lot. I pass the word to Wilfred now from Focuslight.
Thank you. Ivan, you asked one of my questions already. Thank you for the 400 gig per lane. So there is, of course, the notion from different manufacturers, transceiver manufacturers, that with the current technology you can't get the 400G from the laser to the board, let's say. But for the I have a related question. So you showed your EMLs and the CW. So for currently, I think if you look at silicon photonics, I'm not sure if you make, I'm sure you make, I'm not sure how many lasers you make for silicon photonics. So what do you see in the ratio now for EMLs versus silicon photonic based transceivers? What is the ratio at the same speed at 400 gig, let's say, or 800 gig? What do you see as the ratio now between these two domains?
Well, currently deployed, don't quote me on numbers. I don't have the numbers off the top of my head, but qualitatively, I would say that in volume-wise, right now, still being dominated by EMLs.
Okay.
Silicon photonic has been greatly growing over the last, 3 years, 4 years. So that growth is coming fast. When that's a cross curve going to happen, I would probably have to check the same light counting slides that, Vlad has a pretty good sense by talking to everybody.
Yeah.
But I forget what his latest numbers are. But I know silicon photonics is growing rapidly. But my, I believe non-silicon photonic solutions are still higher volume, but not for
Okay.
long. Not for long.
Okay, good.
Yeah.
Thank you.
All right. Any more questions from the audience? Okay. If not, I suggest we thank our keynote once again. Thanks a lot, Christian, for joining
Thank
us
you.
today.
Thank you so much, everyone.
Yeah, very interesting presentation. And with this, I pass the word to our second speaker that represents another very interesting point of view on hyperscale data centers and AI. So Javier Wadwa, the co-founder of Cascade.
Yep.
Hello,
Thank you so
Javier.
much.
Javier will talk about the redefining AI scaling and new paradigm of photonic interconnects.
I hope you can see the screen.
Yeah,
Right?
you're good to go.
Okay, then hello everyone. Thank you so much for the opportunity to present at EPIC Photonics meeting. I'm Bhavya, co-founder of Cascade. Today I would like to introduce Cascade, start with the core problem, the problem the industry is facing, and then I will show you how basically our product is designed to solve it. So AI is scaling extremely fast. Over past few years, we have seen like model size, training compute, cluster sizes have grown dramatically. So what is the challenge basically? What is the industrial challenge it is? So the AI systems is no longer limited by how processors run, I would say, but by how poorly to communicate. Today's data centers, I would say, still rely on copper electrical links, which restrict that communication towards that edges. So these edges, which we call at shoreline problem. So this only allow to hit 30 to 50 gigahertz, I would say, to the bandwidth, and consume excessive lot of amount of power, and also prevent from scaling to, let's say, 100 XPUs full bandwidth. So this interconnect is, as in the graph you can see the gap. This is the basically the bottleneck. So who are we? Like Cascade is a team of like engineers and physicists building deep tech photonic systems. We are based in London and Harwell campus, one of the UK's leading science and innovation hub. Through Harwell and QCC, we have access to expertise in leading researchers and engineers and we are also closely connected with the University of Southampton and Cornerstone. So we're getting that advanced fabrication technologies as well. We have that access towards that as well, and we are also supported by UKRI. So what are we building? So we are building our Gen 4 3D CPU, the core package optics platform that integrates optical input output directly with the high performance compute using advanced 3D packaging. I would like to say advanced 3D packaging here. So in the left side, you can see the state of the art today. Even large companies are forced to place these multiple CPUs engines around the package and to reach the target throughput. With our proprietary technology and the architecture which we have, Cascade can deliver 64 Tbps bidirectional bandwidth with a single CPU. So I would say, like, the universally asked question, does the size matter? I would say, like, the Moore's law would say yes in that regard. So in the right side, you see this is our 3D CPU product which we are offering. So the first product, and built on top of our proprietary photonics innovation and 3D architecture, it delivers very compact, dense optical engines with 64 Tbps of bidirectional bandwidth, making one of the fastest, more power efficient CPU. We achieve below 3 picojoule per bit, and because of the platform is UCI compatible, can seamlessly like integrate ASICs and compute and switch vendors, allowing HPCs or like hyperscalers to deploy Cascade CPU alongside their ecosystem very easily. I would like to tell you more about our technology. So the technology depth is we use SPPs, surface plasmon polaritons, which allow us to build ultra compact photonic devices far beyond the limit of the standard, I would say, photonics. So our current platform can deliver 8 lambdas, like 8 wavelengths, and scaling. We are also scaling to 16 on our roadmap. So the photonics innovation which we are making and which we are doing just not only delivers like today's 3D CPU, and it enables like our long-term vision, which is like disaggregated compute and memory connected by photonic system, as well as for our future solutions for hybrid quantum classical photonics architecture, I would say. So back to the RRMs, like RRMs are like intrinsic wavelength multiplexing we can do, enable cross C-band and O-band operation. On the right side, you can see how the brief illustration of how SPPs are generated. Another key technology I would like to mention here is detachable fiber array connectivity, which enables us to have wafer level optical assemblies. This means the optical units can fully be qualified and tested before attached to the package. So it's really advantages, right? Like which dramatically improves the yield and reliability before and I would like to mention that because of this attachment, the detached way, we avoid the limitations of traditional V group approaches and result to these platform we can do high volume manufacturing, and it's very effective also. So exactly what HPCs and AI data centers require. What exactly this meant for our customers is we reduce, let's say, 40 to 60 lower TCO, like CapEx OpEx, and making it like more compact, faster, power efficient, and also delivering better thermals, lowering carbon footprint as well, and easier system for AI and data centers deployments. Thank you so much. I will happy to take like answers. I can just answer any question if you guys have.
Thanks a lot, Javier. Very interesting development you're doing, and yeah, I wish a very good success to Cascade anytime soon. So yeah, now this is open for questions. So please raise your hands if you have any doubts to express. Javier, I'm wondering myself. So yeah, what's also the timeline you're planning for the development of the system? And yeah, what's your take on this? The big boom of the AI data centers coming already now.
Yeah, that's that's a good question, and quite good question in the industry as well. People are lots of like asking these days. So I will say 2 years from now, we can deliver the product, and we are making our IPs as well, and we are prototyping. We're in the prototyping stage. So, and industry is also ready, as our speaker also mentioned.
Okay, okay. So is there anything that our community can support you with in your developments?
For sure. We are open for collaborations. We are happy to connect with HPCs, and anybody from the technology, from the component level would like to reach us. It's very nice, and let's check through the community as well from Epic community. Seems very nice, interesting people. We'd love to talk, yeah, for sure.
Okay, okay, sounds good. Thank you. I pass the word to Enika from Enika Partners.
Hi. I'm very interested by the detachable fiber attach. I have a question. Do you have some, what are the level of loss that you have, and is it reproducible?
If I understood your question correctly, like you wanted to say what the advantages which we are providing, right? Yeah, I mean, with the flaw, it's like it's better than the traditional ones which we are using, and we can detachable very easily, and it's better for the future scaling. We can have on the wafer level assemblies as well. We can do that, and more for high volume manufacturing, less cost, and these are the advantages which it will give, and also like grooveless. So this is better in those terms. And also industry is, I think, like from my point of view, industry is also shifting.
Well, you don't answer my question. Is that reproducible?
So in that case, I would say 1.5 dB of roughly running loss. Yeah, but we are also doing some innovations to reduce down to, let's say, 0.5 dB of loss.
Okay.
Does this answer your question, or?
Yes, thank you.
Yeah, that sounds like a good start also. So congratulations with that, Javier. I hope, yeah, it grows better and better. So Wilfred, please, from Focuslight.
Yeah, I have a related question. So I think there's the Enika, the question was, of course, very good already. So you have multiple places where you have loss. So you have in the waveguide itself, in the modulator, you have loss, and in the grading or edge coupler, and then on the detachable fiber. So what is your loss budget? I had the same question basically, but can you say the loss budget of these three parts of your system?
Yes, so that's a very good question, and SPP is a little bit lossy as well. But we have our link budget, and we have considered all these losses, and we are also placing these losses accordingly, and we can just go to 1 kilometer to 2 kilometers as well for the reach side. So we are considering all these losses, and we are in the limit. So our loss link budget consider those losses.
Okay, thank you.
Does this answer your question, or we can go
No,
depth?
not really, but it's okay. We can do that offline.
Yeah, we can do that offline. Yeah, for sure.
Yeah, indeed. So please feel welcome to stay with us until the end of the meeting, and then we have a little bit of a LAMP atmosphere discussion afterwards. And also, I'm happy to connect you with your email addresses. All right. So with this, let's thank Javier again for this very exciting talk, and wish him great success in the future. And with this, I invite the third speaker of this meeting, Ana Belén González, the VP of Business Development at Hyperscale. Welcome, Ana. And Anna will talk about the reconfigurable optical networking for AI clusters.
Yes, okay. So thank you very much for your presentation, Ivan, and for the invitation. It's always a pleasure to be talking in an EPIC event, my former organization, right? Yes, and today I'm going to talk about where is the photonics, right? In the hyperscalers. So photonics for hyperscalers. And for this, first of all, I would like to start defining the scope of this presentation. Because, well, let's say that when talking about the OCS, the optical circuit switches that we are doing based on silicon photonics, yes, they are for data centers, but let's say that they are for AI cluster data centers. So in fact, this presentation will be based on AI cluster applications and how OCS fits here. So first of all, I would like to explain a little bit how it works, the scale out and the scale up network. So here you can see in this figure a representation of a data center. Christian from Lumentum already explained it a little bit, so I am going to give just a few words about this. You have all the processing units inside the rack, right? And then you have different type of switches. For AI clusters is the typical NVLink from NVIDIA, or also the UA-Link from AMD and Meta. And then these switches are going to connect the GPUs or the XPUs inside the rack. And this is what we call the scale up. Then we have the other part of the network that is the scale out. In this case, what this network is doing is to connecting, for example, to processing units from two different racks, or also to connecting the processing units with the user, right? With the person that is waiting for ChatGPT to write her email. Then, right now, what is happening is that AI jobs are running in normal data centers, right? In data centers with this type of structure. And where is photonics here, right? Photonics is in the fiber optics that connect the scale up, and also in plenty of transceivers, because all the connecting nodes are working in electronics. So they are electronic packet switches. what we were saying. We have the scale-out switches that are the InfiniBand, is from NVIDIA, and then the rest of the Ethernet switches, and then the scale-up switches. And here, please have a look to the market, to the interesting market. This is a light counting market report where they show, this is in particular switches for AI clusters. They are showing here like 16 billion for 18 billion in 2030 for scale-up switches, and also another 14 billion for the Ethernet type for scale-out switches. So that is a good part of the market. And now, how fits OCS here? Well, let's say that there are requirements that I'm going to explain in the next slide. So there are requirements for more bandwidth, for more GPUs inside the racks, and for this, for more flexibility. And this is why optical circuit switches are now getting into these networks, the scale up and the scale out. Today I'm going to talk only about the scale out because, well, the time was limited. So, and I also want to highlight this market report from Signal AI. It was at the end of 2025. They reported this 2.5 billion for the estimated market of the OCS in 2029. That was a 40% of increase since the forecast in January. What means that well, the market has been moving a lot at the end of last year. So yes, 2025 was the year of the CPO. And in 2026, we can see, I think we will see already some big players mentioning OCS for the first time. So what are these drivers of the adoption in AI clusters? Well, as I was mentioning, there are some connection limits. The copper physically cannot send bandwidth very far away. So then now we are limited to 72, maybe 144 GPUs per domain, and we require domains with 1,000 GPUs. Also reliability, right? What happens when you have 1,000 GPUs? That, well, the failures in hardware are likely because there is a lot of hardware involved. This is why in these training jobs, or well, AI jobs, just one failure is going to impact the entire training and is very costly. Also power limits. So GPUs are power hungry, and this means that you need to reduce the power consumption in the rest of the network as much as you can. And for this, we are proposing OCS. With OCS, you know, you don't have bandwidth limit, it's transferred to bandwidth. You can put fiber optics, and then you can connect as many GPUs as you want. Also, you can reconfigure very fast an OCS because it's connected to the software-defined network, to the control plane of the AI cluster. And then, well, you are reducing the power consumption, not only because you are utilizing more the GPUs, which is a very expensive resource, because you can reconfigure the data center, but also because you are reducing a lot the number of transceivers, so the number of electro-optical conversions. Just a few examples of these scale-out networks. These are some published works, so from key players. In this case, because the importance of the resilience of failure in AI jobs, NVIDIA is putting the OCS between the layers. Well, in this case, they are adding to the CapEx for this redundant equipment. So they are using OCS to connect with this redundant equipment, and this is the case of the spine replacement. So this is the application that Google has been pursuing during the last years. They are replacing the entire spine by OCS. In this way, they can also avoid the failures, but they also have other benefits that I'm going to explain in the next slide. Here, this is what we were talking about NVIDIA. They are using MEMS-based switches, like the ones that Christian was presenting at the beginning of this meeting. In this case, as I already explained, what they are doing is that they are taking advantage of the reconfiguration capabilities of this MEMS device to reconnect. Well, first they recreate a failure in one of the transceivers and in the middle of a machine learning job, and they claim they are able to reconnect with the machine learning job in 4 seconds without or with a minimum impact in the job. And they are doing this using the software control network or the control plane. These are some of the advantages that you can get if you replace the entire spine using OCS, as Google did. One of the advantages that they highlight in this article is that you have, well, once you want to make an upgrade in the hardware of your data center, you cannot upgrade to a higher bandwidth when the spine has a lower bandwidth. Right? In this case, you will be derating your data center. So if you are using OCS as a spine layer, you are able to add new servers even if the data rate is higher. So this is a problem that Google solved. And in addition, they got 5 times higher speed and capacity, 30% reduction in CapEx, 41% reduction in power, and they are able to reconfigure and to optimize the topology of the data center for depending on the traffic needs. This is the topology engineering of Google. And what happens if you have even a faster OCS? I mean faster, I mean a silicon photonic OCS, like the ones that the Photonics are developing. In this case, you can even change the topology of your data center, of your AI cluster, in the middle of a training. This is a work from KDDI where they use it for doing this. They use it a very fast reconfiguration optical circuit switch, and they were able to accelerate 8 times a training job by reconfiguring in the middle of the training job. So by adapting the topology to the traffic needs of this job. So this was all the part of the articles. Now I'm going to talk a little bit about the device that we are developing. So I'm very happy to introduce you here our optical networking engine. Is a 1U rack, a silicon photonics optical circuit switch. You can see here a sketch of the device to highlight the device is lossless. We have added optical amplification, and we are able to compensate per channel completely the losses that silicon photonic introduces. Even for doing that, right, we incorporated a monitoring array. So it's not only that you can reconfigure perfectly and you have the complete control of the chip through the SDN layer, but also you are able to monitor in real time what is happening in each channel, and even so you are able to set plenty of alarms, and even you can locate the issue. So what is the link that has a failure? That is something that is challenging in big AI clusters. Just a bit of the performance, so you can see what a nice spectral response, very flat in the entire O band. So we are compatible with DR, FR. And yes, sub-millisecond reconfiguration time. And then if you are going to ask for the crosstalk, you can see that we almost cannot detect it. And very low impact in the bit error rate, 1 decade of impact in the bit error rate. And just to finalize my presentation, just to say, I would have loved to talk a lot about our software layer because we put a lot of work on this. But well, just to say that we have developed this software layer based on GNMI and NetConf protocols, and that for more standardization, we are working with the Open Compute project, and we are leading, together with Lumentum, by the way, we are leading this initiative for standardization of the software of the OCS. And that's it. Thank you, Ivan.
Nice. Thank you very much, Anna. Great presentation, as always, coming from Hyperscale. Yeah, so that's a very interesting product, I'm sure, for the revolution in the AI data centers. Are there any questions in the audience? Yeah, in the meantime, I'll ask you, Anna, of course, the epic question. So how could we support you in these developments?
Okay, so yes.
What are the missing elements?
Well, there are no missing elements, but of course, there is always room for improvement. And as always, the fiber attach. So now we are in our, we are using 32 fibers, right? Because we are developing a 32 by 32 optical circuit switch. But after this, we go for 64, 128, and maybe even beyond, right? So as always, a better fiber attach with less losses and more reproducible. That will be, yes. Well, as I have been hearing in the rest of events, no, for the last 5 years. This is the challenge, right, in photonics.
Okay. In fact, I think I have an interesting solution for you. We will discuss later. Wilfred, did you have a question?
No, it was answered. Thank you. Thank you.
Okay. All right.
Anna knows what to say.
You were going to ask me about losses, right, Wilfred?
No, the port count. What is your
now it's 32. Yeah. And then we have already, so we are shipping now the 132, this 32 by 32. Then we already have the 64 by 64 at our lab, and they are testing the chip, and it's looking very good. And it's going to be ready later this year. And we are already designing the 128. That is a 128. Wow.
Very impressive. Nice. But you're fully focusing now on OCS, because when you started Hyperscale, you had different foci, let's say, different areas you worked on. Yeah.
Yes. We are now so we are using the same building blocks, the same photonic integrated circuits building blocks, the MMIs and the crossbars and this type of things. However, we had to move from the C-band to the O-band, and now, yes, so we had to move all our building blocks to the O-band, but it didn't take that long, and now, yes, we have an O-band OCS, lossless.
Nice.
Cool. Good.
Okay. So what's happening here is I know is that Wilfred cannot wait to start his own presentation. So let's thank Anna again and pass the word to Wilfred now. So Wilfred Noel represents Focuslight, and he's a chief scientist and a business developer there. And he will talk about realizing the high data rates in data centers, more than just optical challenges.
Well,
and you have 3 extra minutes.
Do you see the right screen? Do you see the
need to make it
preview
full
or the main screen?
No, we have a preview.
So now it's better?
No. Okay, now it's good.
Now it's good. Okay. So yes, so I like to give, so similar to Anna, I like to give a little bit of an overview first, and to Lumentum. So where the data centers are from our point of view, and what we see from our clients, what we see there. And so let's say first a couple of words about Focuslight, and then I go deeper into. So Focuslight is actually a company that started off with lasers and then integrated optics into their portfolio. So we actually used to be a laser company, building laser modules, laser systems, and then we added all the micro optics. So we own 4 major micro optics manufacturing technologies. So we have the etching, like the wafer level etching, we have molding in-house. Then we have, for consumer electronics, we have the imprint optics. It's not shown on this slide, but this is more for consumer, where we make hundreds of millions of lenses per year. So it's a bit different than this community. And then also we do all the technology that is required for large laser systems, so the beam delivery optics and the beam shaping. So this is more for processing and semiconductor industry. So really we do all types of micro optics, the laser systems and everything. So what I wanted to actually point out with this slide is that we are used to co-designing. And co-designing is the key to successful product. And I will mention the word co-design probably on every single slide today. And because CPO and other technologies, they all need to co-design everything, everything that is involved in the product. So you can't just make it modular anymore that easily as it used to be for transceivers. So, I mean, we mentioned already scale up, scale out. So currently everything is copper, then co-packaged optic will come eventually end of this year with Spectrum X from NVIDIA, and then with others. Broadcom has presented a lot of these things, and there are other companies who keep presenting their CPO solutions. And then, of course, for the scale out, that is basically based, as just mentioned previously already, by optical transceivers 400G, 800G, and higher. The obvious light counting and signal AI slides, I have those too. And what is important to look at here is that the cables will not disappear. So the red part are the cables. So there will be still a large portion of the scale up will be done on classical cables here. So this is not only optics, it's also just pure electronic cables. And CPO will probably start around 27 and with ramp up in 28. And then the Ethernet transceivers will still dominate the market in the data centers. And here, if you look at the recent presentation from December from Signal AI, this is for telecom and DCI, so the datacom or data center interconnects. So in between data centers, you need pluggables now as well. So there used to be only embedded solution, or majority was embedded, and they will be slowly replaced by pluggables. So in telecom, there is now the same trend like in datacom. They're using pluggables now, coherent pluggable solutions. This is very fascinating. There was a very nice webinar from Signal AI just before Christmas. And there was this PEC event from Optica and APC from the Photonics coalition just in October, November this year. And Arista presented the forecast they see for pluggable transceivers, and they estimate 100 million transceivers, and in the next 2 years per year, so 26, 27, we'll see a huge ramp up in pluggable transceivers, and this can only be done by automation. So like I said before, I'm not going to talk only about optics, but also everything that needs to follow. And this has been already pointed out by all the users of this technology. So they see, in order for the industry to meet all these demands, a lot of new things have to be done. Not just better optics, better lasers. You have to put the whole infrastructure in place. You have to have automation. You have to have every single component supplier has to be ready or capable of the scale up. And CPO will come later, but we will see when. Huh? So this answers also the other question that was asked earlier about the 400G per lane. So 400G per lane will come sometime in 28, 27, 28 probably, but it will require a new connector because of the losses. So if you have 400G, you have huge electronic impedance losses, and these losses have to be somehow handled. So that means in just moving from 800 up to 8 times 200G, it was basically some type of engineering, improving the technology, reducing the losses on the optic components and the lasers and the reliability. But for 400G, you have to make everything different. And and if you go and look at the and how this has to be done also by co-design. So you have to co-design the connector now with the optics and the laser. So you can't just say, okay, we just do this one part and the other part will be developed by somebody else. No, it has to be a common effort. So I asked earlier the question about silicon photonic space versus EML. So you have the free space and the CWDM systems, and you have the silicon photonics. So for now, still the left part is dominating in the business, but the right part is coming very strongly, especially for 1.6 tera transceivers. And what we do here, we do the micro optics for either the lasers or for the fiber couplers, or here for the couplers into the photodiodes and the collimators. So all of these type of micro optics and large arrays that are required, this is one of our products that we do. And for the lasers, there's more and more new things coming that have to be considered. So if I look at the NVIDIA slides that keep showing, so there's Quantum X and Spectrum X. So Spectrum X is expected to come this year, Quantum X later. From what I've heard or gathered is that the Spectrum X still works with attached fibers, where Quantum X already needs detachable fiber connectors. And you see, if you look at the mechanics, so this is not a simple system. So there's a lot of mechanics and thermal and optical interface to be considered. So it's not just the little drawings that we see, the schematics. If you look at the real system, there's a lot of things happening here mechanically as well, and that has to be co-designed with the other parts of the system. So NVIDIA says, okay, there needs to be more photonics in their scale up and scale out systems. So of course they talk about the TSMC COUPE process mostly, but you see it's a consortium solution. So that means you can't just have one company finding a solution and then hope the other solves the other problem. So it doesn't work anymore. So basically, co-packaged optics is an ecosystem approach. So you have all these different ecosystems, and I consider EPIC kind of an ecosystem here. They're bringing companies together. Same like the PIC Summit. They will also have an event next week in Sunnyvale just before Photonics West. Then there's the Advanced Photonics Coalition. And of course, the semiconductor industry has now discovered photonics. So there's no semicon event anymore without a photonics session or even a special workshop on photonics. So this has been, and Anna mentioned Open Compute Platform. They didn't used to bother with optics. Now they have a special photonics section as well. But what is important in these ecosystems, they're also competing companies in these ecosystems. So there has to be an agreement on interfaces and technologies. And currently this is coming, especially the APC is pushing this. SEMI, of course, has always been pushing standards, but we have to see how this ecosystem will be able to handle this. And if there's an island solution, it will not work. So if you look at it a little bit more detail, so if you look at this design of a typical CPO-based system, you have here a continuous wave laser, you have some silicon photonics, you have the switch. And I don't know if you guys are aware, but the switch typically needs a few kilowatts. So this is a kilowatt thermal heater, basically, on a substrate. So you have to get rid of all of this heat. Photonics doesn't like heat. VCSELs don't like heat. MRMs don't like heat. So there are a lot of heat that has to be dissipated. So even so, this optical engine only needs 7 watts, so the switch needs kilowatts. So it's an interesting comparison here. So, and in order to have this 1.6 terabyte or terabit better that goes in and out, you have to really co-design everything. So that means for the EIC and the PIC, it's not enough just to look at these two. So the photonics and the drivers on a single substrate, it's not enough. You have to co-design the FAU, so the fiber array unit, so the optical detachable connector. You have to have the TSVs, the feed-throughs to the PICs. You have the hot electronics. How do they impact PICs? How do they impact polymers that are commonly used? So that means then there's always, wouldn't call it a battle, but the discussion, grading couplers versus edge couplers. So we have a solution, a nice solution for edge couplers that I will show in a minute. And then there's the whole backend processing. So basically, if you look at CoVoS from TSMC, they built the EIC and then they put the PIC on there, but then they run the backend process of the EIC, and the PIC did not used to be compatible to this backend process. So you have to look at this. And then on the other side, if you look at the laser side, and this is more also the EPIC community. So you have these high power lasers that were mentioned from Momentum, 400 milliwatt. You must not have any polymer in your optical train. This is such high power density that the AR coatings, any polymer interface in the optics will suffer. So all the requests we get for making optics for external laser sources, they have very high demands on the optical interface, no polymers. And then in order to get these high laser powers, you have a very high NA, very highly astigmatic laser diode. So you have very high order A spheres. And then you have the on-chip SOA, so the packaging, the heat that is there. So then in parallel, quantum dot lasers are coming, which are thermally stable, don't seem to need isolators. And all of these systems will have also very highly astigmatic beams. So somebody has to handle this. So we look at special micro-optics for these systems. We also do substrates. We are, like I showed in the beginning, we come from the industrial lasers. So we have substrate that are used to kilowatt lasers. So that means 400 milliwatt should be very easy for us to handle. So that means there are new thermal and optomechanical challenges. It's not just a photonic solution anymore. It's a system-based solution. And then you have to design these two in mind. So if you come with a high power laser and you have a grating coupler that gets nonlinear at 300 milliwatts, you can't use the grating coupler anymore. So that means you really have to look at all these things, how they work together. And this is very exciting, and it's very nice to be part of this development. And when I look here at the laser module, so here we do the optics, as I said, we do the substrates, we work on the high power substrates and the astigmatic optics in order to get the light where it's supposed to. So for the system, if you look at the whole TSMC-based COUPE system, you have here the grating, you have some oxide, you have this integrated microlens. So what we do here, we work on these optics on the FAU, and all these FAUs, all these systems will look very different. So we make the components here, we're not making FAUs, but we make the components that go in there. And then our solution to this whole system is we have now micro optics that go into the trench in the edge coupler here. So these trenches are already in there for wafer level testing, and we provide these micro lenses with the microprism. They are less than 30 microns in height. They're very small. They fit easily in these trenches. These trenches are actually much bigger than our micro optics, and we can adapt to the same FAU that is used for the COUPE-based systems. And the other thing that you see more and more are these port counts are really increasing. They're 36, 30, 42. These are huge port counts, and the current FAU technology is not made for this, so it has to be developed for these high port counts. And one word again to the detachable optics. So this was asked before. So we put this micro lens into this trench, and then you have some type of receptacle that is actively lined to this trench, and then you come with a fiber connect on top, and then the light couples into the fiber. So you can then reverse this whole thing, and it has to be detachable. And then there are thousands of fibers that are attached to these ports. So that means there's huge mechanical impact on this receptacle, which is somehow glued on this PIC. So you have to really think of a full mechanical solution here. And the port counts are much higher than in transceivers. And so we work on these high port count V-grooves now. So that means that they meet all these specifications, and people are already thinking about multi-level V-groove arrays. So this is something we look at. And I like to close with this. Again, co-packaging means co-design. High lasers have constraints that we don't know from the pluggables. So the high port counts require new technologies, new supply chains even. And the agreements on the optical and mechanical interfaces have to be done so there's no island solutions. Because like in semicon really flourished in the past when island solution was removed and replaced by standards. So that means island solutions stop the progress and or slow down this progress, let's say, and create high risks. So if there's a flaw in one of these island solutions, then it will just not work. So that means we have to work together here, and that's why EPIC is one of these organizations to push this. Thank you for your attention. I think
Thank you, Wilfred.
A couple of minutes longer. I'm sorry.
No, that's perfect. So thanks, for a very nice presentation and for the good words about EPIC. Indeed, I mean, you shared some very interesting things. I'm actually wondering myself, so the Spectrum X, that the product of NVIDIA you mentioned, so is it already public? Who will make this detachable optical connector for them?
No, we don't. Well, there are different names mentioned there, but we don't know exactly who it is. So they're different. It is probably somewhere in Taiwan or China. That's what we see. So Foxconn, TFC, one of those companies will probably do it. But there are others. Well, if you look at if I showed earlier here, so there's companies here that make connectors, Senko and Cornings. They make these, and then Foxconn is here. and TFC is mentioned here as well. So these are all companies who make AFAUs and connectors. So, but who will be the one in the spectrum? I don't know. A good question. Yeah.
Yeah, and of course your argument also about the co-design of the electronic and the optical part is very strong. So, are you maybe looking into building a collaboration for the same purpose of co-designing these two things?
So we actually are already discussing with companies here, and so we are, like I showed, we offer these components that are part of CPO and FAUs. So we're talking basically to everyone right now in all across the globe, not just in China and Asia. So also in the Western world.
Mm-hmm, mm-hmm. Yeah, exciting
but very
times.
good question. So it's not very clear yet who will do what, and the thing is, there's no perfect solution yet. So people kind of trying to solve problems along the way. So this is very, very interesting, actually.
Oh, indeed. I see a question from Annika. Please, Annika, go ahead.
Yes, I have two types of question. You just mentioned freeform optics. Do you implement
Free space? Or which one? Oh,
yeah, freeform optics.
Yeah. Okay. Yes.
Okay. And do you implement them in your CPO? And the other question is about the ecosystem, because as you know, the world is not so soft today. So how do you see the geopolitics, I would say?
Very good question.
Do you see some solution by areas from the US,
Yes,
from Europe and
definitely.
Asia, or
Yes, so there
what's
is
your
actually the Semicon Alliance is focusing on Taiwan currently. Taiwan, maybe a little bit East Asia, and then there's the APC is more focusing on the Western world. They do have some Asian companies in there as well. So that's a very big discussion within these ecosystems to also, there's TSMC versus Global Foundries for obvious reasons, not just for technology reasons, also for location reasons. So this is also very, very hot, these topics, especially with what happens these days. And yes, so there will be different ecosystems, different solutions based on geopolitical frameworks. So, but that is definitely, and for the free space, so we don't do CPO, but we make the optics that go into CPO. Yes, and we can have different optical features. So, like I said, we have 4 different technologies in house, and we will choose the one that is most suitable for the process. And this can be could be high order A spheres, could be double-sided lenses. So we really make crazy designs these days, or our client do them, and we just manufacture them. So this was a very good question, especially for the external lasers, for the high power lasers. They are such very astigmatic beams, so we have to make really new micro optics for these types of lasers. Good question. Yeah.
Have you specific treatment from high power lasers?
No, we use, well, like I said, we come from the high power industrial lasers, so currently we're okay. So,
yeah.
But yeah.
Okay.
Okay, let me ask Amir from SUS Microtech. Please go ahead.
Hi, yeah, very nice presentation. Thank you. Really good stuff in there. Maybe too detailed question, but can you comment on which lithography technology you are using for your MLA or your couplers, if you can comment, or if you have
of course. So of course, I mean, we used to be in the same company. I don't know if you know.
Yeah, definitely.
Yeah, so we still use the same technology as before, though it hasn't changed much. So okay. Yes, we use standard. Well, we have actually, depending on the products, most of our products are done with standard mask lithography, but we have a few products where we have access to stepper. So that's a very good question. Yes, yeah.
Understood. That answered the question. Thank you.
Yeah.
Okay, and the last question from Dieter from Shangchun Institute of Optics, please.
Yeah. You mentioned quantum dot lasers in your one of the second last slide, I think. Did you consider working with Illuminome, which is a leading supplier of quantum lasers in the world and situated not so far from you?
There's very
And the
close to
advantage, let
our
me just
Dortmund
address
facility.
one more advantage. It's a gallium arsenide-based technology,
Yeah.
which reaches beyond 1.3 micrometer and is, of course, much less expensive than any indium phosphide-based technology.
So I know Alexei very well. Yes. So answer your question. One of the founders. Yes. So yes, quantum dot lasers, they're definitely, so InnoLume I know very well. Yes, and they're very close to our Dortmund facility. So I'm in Switzerland, so I'm with Focuslight Switzerland. But of course, I know InnoLume and Dortmund very well. Yes, very good company actually. Yeah.
But my question was a different one, not whether you know it, whether you're going to use these lasers.
Well, it's our clients who decide. So we just make optics. So we would provide optics to the system, and then our client makes the qualification. Yeah. Yeah. So we don't make transceiver lasers. We make industrial lasers, but we don't make lasers for transceivers. It's actually a good question that keeps coming up. And but we make all the components that can be used for transceiver lasers, like the substrate. The
I mean, it makes the system much less expensive due to its insensitivity to back reflection.
Yes, you have no, you have no isolator.
So the system cost goes down.
Yes. Yeah, I mentioned that on my slide. Yeah, so very good point. Yeah.
Okay,
Are you working yourself on the quantum dot lasers, Dieter?
Of course, I'm one of the founders of InnoLume.
Ah, that's why.
And still holding shares.
Yeah, very good.
And right now we are getting Andy Berchtolzheim, who will invest, and it's going to explode very soon. And we're working on quantum dot lasers for LIDAR systems at 1.3 micrometer, at 1.25 micrometer actually, which is an air transmission window. It's much better than 910, what is the wavelength which is presently used. It's again another application completely different from the one we're discussing today. But the same basic technology, that's the point. We do have the technology, and we do have now we have only a few companies in the world producing such lasers, and the largest one is InnoLume.
That's correct. Yes. Yeah.
There's close to 80 people working there.
Yeah. We follow their history very precisely. Don't worry. So thank you very much for your question, Dieter, and thanks a lot for the great presentation, Wilfred. Yeah, a few very interesting messages you shared with us. So with this, I'd like to invite the next speaker of today's session, Ian van den Wieker. So he's a business development manager from Chilas in the Netherlands. And Ian will talk about the O-band tunable laser for data centers.
Yes.
Not to drop the topic of the lasers.
Thank you for the introduction. Can everybody see my screen?
Yeah, good to go.
Hi, I'm Ian. Good year to everybody first, and the best wishes, and I hope everybody turns out in a successful new year. I'm here today to talk about tunable lasers for data centers in the O-band. I'm Ian. I'm business developer at Chilas. I've worked here since almost 5 years now. Started out as a test engineer, and later on took over the business side of the business. So Chilas at a glance, we founded in 2018. 2020, we released our first tunable laser at 50 nanometers. And in the years following that, we broadened our scope. We have multiple distributors all over the world. And since a year or two, we sell high-performing tunable laser modules fully integrated. We're led by photonic industry veterans. Our CTO, Dimitri Gessis, as you can see here on the left, is the main proponent for the development of the O-band laser. And if we dive into the unique technology that we have to offer here, as you can see here on the right, I'll point my laser pointer, we have the laser itself. So we have an indium phosphide gain chip, which we butt coupled to a silicon nitride feedback chip, on which we have 2 rings, which we tune to exploit the Fourier effect. That way we can tune the laser over a wide range, sometimes exceeding 100 nanometers. Due to the silicon nitride feedback chip, we have ultra narrow line width and high output powers depending on the semiconductor optical amplifier that we use. Now, on top of those rings, we put heaters, 2 to control both of the rings, and 1 to control the phase of the light in the cavity. And by simultaneously tuning these lasers, we can get a nice output over the full gain bandwidth of the laser, going down to resolutions of either 1 megahertz. Out of this, we make a nice product. We put the chips inside of a butterfly package, and then put the butterfly package inside of a tunable laser module, as you can see here on the right, the Atlas. The Atlas is defined by having a broad wavelength range, such as 100 nanometers. Our most mature products are at 1550, 1600, and 1700 nanometers. And we can switch the wavelength on a predefined grid within 20 milliseconds. Our standard products comes with a 10 picometer grid, but we can also change this to any type of channel or frequency that the customer wants. So as we see that there is a major push for O-band lasers coming down with the surgence of AI, we decided to go develop the 1310 as well towards the O-band, and that's what I wanted to talk about today. So as we see here, we have some typical results that we see in the L-band. As you can see, we see a nice power output over the full range and a high accuracy even within 0.2 picometer over the full range. And then we go to the 1310. So our initial results are that we have a tunable laser going from 1265 nanometers to 1365 nanometers, on which you can switch within 10 picometers over the full range. There's a power consumption of around 5 watts and a power output of 10 dBm. The module, as you can see here on the right, can be provided with an integrated isolator, providing lower return losses. So the module comes as a full turnkey solution. We can provide it with an adapter for USB control. Comes with a Python library for making your own software and connect it into your own product. The module is always fiber coupled. There's a modulation input if you want to do some wavelength locking, and there's an analog output for sort of sweep synchronization. So thank you all for listening to the presentation. If there's, I would like to know if there are many questions for this. If you're ready to tune in together, let me know and we can discuss further.
All right, thanks a lot, Ian. Great presentation, and I see there's a question already from Ahmad. Go ahead.
Yes. Yes, hi, thanks. Thanks for the presentation. I have a question about the relative intensity noise for these lasers. Do you have any measurements on them?
Currently, no. We get a second batch of chips in April, then we can do those measurements as well, but we expect it to be similar to our 1550 modules, which is around minus 145 dB at 1 megahertz.
Okay, thanks.
Okay. My short question, Ian, is what's your peak on the above mentioned quantum dot lasers for the same O-band?
Well, there's the great surges in demand for it. I'm not sure if the module that we have right now could be suitable for that, but it's certainly a good lookout. Yeah, I'm certainly going to look into it more. Yeah.
All right. Okay. Well, thanks a lot for sharing this with us, Ian. Great presentation. And I'd like to pass the word to our next speaker then. So Chris Maloney is the managing director of the US operations of VPI Photonics. And hello, Chris. And Chris will talk about a system level approach to CPO, LPO, PIC design for hyperscale data centers.
Yeah, thanks, Ivan. Thanks for the opportunity. Yeah, as mentioned, I'm Chris Maloney, located in the US, but VPI Photonics, our headquarters is in Berlin, Germany. So yeah, today I want to talk a little bit about, we've seen some of these background slides already today, but just driving home the point, as AI machine learning workloads increase, we're seeing that increase in power demand for data centers as well. I like to track this each year, and the projections are staying somewhat consistent, whereas in it's projected out to like 2030, we should see about a 3x increase in power demand, really driven by those AI workloads. And so this is where photonics comes in, right? Driving the need for those efficient interconnect solutions. So optics and photonics, play a role there, and I'll get into it a little bit as we talk about, some of the, data center interconnect solutions, how optics are used today, what does the future look like? But if you're not familiar with, just general data center networks, there's different link lengths in the network. And so you might be working, connecting international data center sites that are hundreds, thousands of kilometers apart from one another, or you might be looking at links within the rack, could be tens of meters together, connecting them. And each one of those link lengths requires a different solution. So for longer links, you can use coherent optics, where you can include digital signal processing, which might be a little bit more expensive of a solution, but that's tolerable for longer link lengths. Whereas you get into the data center or connecting data centers together, maybe on the same campus, you'll need intensity modulated direct detect solutions. So a cheaper solution, more cost effective, less power hungry. And right now, inside of the data center, inside of the racks, copper interconnects are typically being used, but as data rates increase, the reach of those copper interconnects actually gets shorter and shorter. And so the only way to get past that is either to increase the power or move to optical interconnects. And so that's what we're getting into today. That's what all the discussions around. Some of the technologies that are being talked about today, we've heard about co-packaged optics, but there's also linear drive pluggable optics. And so I just want to talk about some of the trade-offs. I'm not saying we're going to pick one or the other. I think both of these solutions will be used in the future. And they each have their own subtleties to it. And I actually like Wilfred's point before about co-design, because this becomes more and more important as these types of solutions are discussed. With the linear drive pluggable optics that you see on the left here, you can see the optical transmitter and receiver are actually on the pluggable transceiver, and those are connected into the rack, and there's some electrical connection that brings you to the host ASIC. So that one of the key benefits of that is that it leverages this existing pluggable form factor. So if there's a failure or if you'd like to upgrade, it's easy to just swap those out. And they are a lower power solution because it actually removes the DSP from the transceiver. But what that does is it shifts your design margins to the electrical and optical domain. So you need really linear components within this. And the interface between the electronics and the optics, they start to play a role in your design as well. So co-design, electrical optical co-design really becomes mandatory at this point. When you look at co-packaged optics, some of the benefits we already heard, maximizes the bandwidth density, improved input-output power efficiency, but failures can be unforgiving. So reliability becomes very important. And then the packaging constraints. We've heard about, the thermal impact of being placed so close to the electronics. The thermal management needs to be controlled, especially for your micro-ring modulators. And the entire co-packaged optic really needs to be, the photonic integrated circuits within it really need to be optimized for full system level performance at this point. So we're really moving from, historically where we've focused on designing your device or your component and having specific metrics to reach, your spec, to designing your PIC and taking into account the full system level interactions, whether it be the thermal implications and co-packaged optics or the relationship between the optics and electronics. And so you've seen this slide already. I'm just driving home the point. Silicon photonics is being adopted by the industry. Co-packaged optics, micro-ring modulators are being used in this Spectrum X device. And at VPI Photonics, we're trying to stay ahead of the trends here. So we already have available in our software representative architecture, system level architecture of this type of link. So I'll just walk through this if you haven't seen an architecture like this before. This is an 800G WDM PAM4 link. It includes the silicon photonic micro-ring modulators. And just going left to right, you can see you have your lasers here. So in this case, this actually represents an array of lasers. So 8 different wavelengths, they're multiplexed together. And then we have a chain of micro-ring modulators. So these are all models that we've developed. And this ring modulator, it's driven by an electrical PAM4 driving signal. And so we're going from the electrical domain to the optical domain in this case. That signal is passing through a single mode fiber. It's multiplexed together by another photonic integrated circuit. This happens to be a chain of ring resonators, so three ring filters to do add drop of different wavelengths. And there's an array of receivers as well. So each one of these contains a photodiode, some electronics, feed forward equalization to do some of the compensation, and then the bit error rate calculations. So that's a typical system level schematic. And one of the challenges comes, it's typically one team working on the optical system and one team working on your photonic integrated circuit that's used within that system. And so they might be using different tools. They might be designing with different metrics in mind. But at the end of the day, that photonic integrated circuit needs to be designed within the full system. And that's kind of where we come into play. That's some of our strengths, is we provide solutions that allow you to do that all within one design environment. So it brings those two tools together, allows these two teams to interact very easily. So if you take a step back for a second, typical PIC engineer role, they'll be the one who are doing the characterization and tuning of the different photonic integrated circuits, whether it's the microring modulator, looking at your free spectral range tuning, extinction ratio tuning, the channel tuning, or the ring resonators, looking at your bandwidth and channel tuning as well. But these considerations can no longer be evaluated just in isolation, because each one of those choices you make that impacts the power of the system, the bit error rate, the T-dec-Q, and those decisions at the end of the day impact your full system level performance. So co-design comes into play here. And now if you put yourself in the role of your optical systems engineer, what are they looking at, right? They're looking at different probe points through your system. This shows the optical spectrum of those lasers that are multiplexed together. So they've considered the channel spacing, the line width, the power of the laser. What does that spectrum look like after they pass through those ring modulators? And on the receiver side, all of those decisions and optimizations, they roll up into your eye diagram. So you can see representative eye diagram of just one of the channels. And each channel has its own interactions going on as well, whether it's with the channel beside it or other interactions. And so you can evaluate the symbol error rate for each channel index. So this full end-to-end system level performance, it really needs to include the device optimizations together. So really relying on that co-design, one environment to do the end-to-end simulation and bring it all together. You can even take this one step further, and we do have the electrical models in our software, but if you're working with your electrical engineering team, they might be using a different tool. Let's say maybe Keysight ADS. That's something we've worked on with Keysight, and you can actually call this solution directly from their interface as well. So it brings all the teams together for a nice workflow. I'll leave you with a bit of a teaser here. This just shows a full end-to-end LPO system based on the recent LPO MSA. So we have this available as a starting point, as a template, so that you can bring in your photonic integrated circuits and start to ask some of these questions, right? What if some of these assumptions about your components are wrong? So what if your laser line width is out of spec, or the RIN noise is higher than you expected? How does that impact the eye diagram, the bit error rate? What if you're going to use a different modulator technology, maybe a thin film lithium niobate Mach-Zehnder modulator? Or going back to Wilfred, what if your connector loss is varying throughout the rack? How do you explore that, and how does it actually impact the system? And so all the answers to those questions, it really requires systems level thinking and a systems level model to explore it. So Ivan, to get ahead of some of your questions, what can we do for you? Providing this design workflow that turns your PIC designs into actually system validated components before you go and invest in silicon or committing to different hardware. And what we're looking from the industry is for some more of these challenges. Bring us your real architectures. How can we work together to create some templates to help model the systems that you're working on? Or if you're working on an individual component and you want to understand how does this fit into a hyperscale data center system, these are the types of things we can work together on and collaborate. So yeah, I'm open to any questions at this point as well. Feel free to reach out to me. I'll be at Photonics West and OFC coming up. You can see a workshop that we're going to be running at OFC as well, if anyone's curious.
Okay, thank you very much, Chris. Great presentation, as always. I'm afraid you left me out of questions, so I pass the word to Dieter from Changshu Institute of Optics.
Oh, Dieter, you're muted, it looks like.
Let me unmute you.
Okay, you hear me?
Yep.
Yes.
Okay, 2 questions. Thank you very much for this very nice presentation about co-design. And the first question is, you didn't talk about EDR, energy per bit, for your co-designed circuits. Do you have any numbers? How many picojoule per bit, let's say across 100 meters, or that is the essential point, one of the essential point. It's actually a killing point, I believe, in the future.
Yeah, I don't have any numbers for you. That is something you can't exactly explore on just the optical side. You really need to get into more electrical modeling.
Yeah, it's a co-design model.
Yeah.
That is what is discussed today.
Yep.
I mean, I do have numbers for co-designed electronic drivers with VCSELs, surface emitting lasers. And in the surface emitting laser area, the trend goes towards narrow wavelengths multiplexing with 5 nanometer distance. And then you can easily, 100 giga is easily achieved with VCSELs. Having EDR below 100 femtojoule per bit, and including driver below 300 femtojoule per bit, will be published at one of the conferences soon this spring. And this is a real competition to the approach you're using here.
Mm-hmm. Yeah, so
it's much less energy expensive.
Right. So that's something you can evaluate with these types of solutions. That falls, at the end of the day, you want to look at the full entire system, right?
Yeah.
The optics, the electronics, whether it be the equalization circuit or the power driving the modulator, that all needs to be included together. From our perspective, from VPI Photonics, we're providing the optical solution, and that would rely on that. The entire, evaluation of the picojoules per bit would fall under the electrical design part of the full system. So we would need to know more information. But for each, let's say if you're using a thin film lithium niobate modulator, we can extract the power that's required for the individual components, and then you would add these all up together as part of the full solution.
Yeah,
okay,
but we're providing really a template for you. So we're following like the LPO MSA I showed. We're following the standards. We're bringing a generic solution into the software so that you can then take it to the next level and actually implement your components or your architecture on top of it.
Okay, Wilfred, please go ahead.
I have a question. Thank you first, Chris, for picking up or basically saying the same like me on the co-design. I'm very happy that we agree on this. So the other point I want to make, the other question actually I have, so we see this, maybe not so much for LPO. LPO is kind of converging now, but CPO is still, wouldn't call it a big mess, but it's very dynamic, let's say. How do you handle this when you have to put it in your systems? Do you make custom PDKs then, or how do you handle this when the product is not standardized? Can you put that in there easily?
So that's a good question, right? So when it comes to we'll say the photonic integrated circuits side of it, we do support PDKs at various photonics foundries. Something that we've done because we've noticed that there is no standard for CPO right now. The approach we've taken is a little bit different, and what we've done is create a PDK framework. And so anyone that's using the software can create and manage their own PDK at whatever foundry they go to. So when you go to any foundry, they don't always have all of the information that you need. And maybe they don't have tolerance data. But as your company goes and does tape outs and you understand you gather your own measurements, you can build those into your own PDK, keep the IP to yourself, and actually encrypt your models. And then you can go and share it with potential customers as well and say, hey, run this simulation in your system and see how it works. So we've tried to be a little bit more flexible in our approach to PDKs rather than supporting every single process. We allow you to manage it yourself. So we opened up the development tools to the users.
That's great. Thank you.
Yep.
Okay. Thank you very much, everyone, for questions. And Chris, great presentation as always. So thanks for joining us, and see you in a week. With this, I'd like to pass the word to the last speaker of our session, Eneka Ediarte Barsun. She's the CEO of Eneka Partners, and she has another very interesting point of view on the topic we're discussing today. So Eneka will talk about co-packaged optics, the next game changer. Please unmute, Eneka. You can unmute, and you
I have
can
to share my own presentation. Sorry, I'm not very familiar. Yeah. Okay.
You can use this green button on the bottom.
Yeah, just let me share. Can you see it or?
No, not yet.
Not yet. Yep. Sorry.
Yeah, no worries. So the way
I
it work,
didn't try it before. So
the way it should work, you push on this green button.
Yeah,
share
no, but because I
bottom.
didn't, I didn't allow the Zoom yet, so sorry for that.
Yeah. So it's share, and then you can choose the window.
No, just a minute. Oh, sorry, I have an issue with my. Maybe you can share the presentation I just sent you, or because I have an issue with my.
Okay, give me a second.
Sorry for that. I didn't try my parameters, so.
Yeah, the thing is, you send us, I'm afraid, the wrong file. You send us.
No, I just sent to Vera, I think, the PDF.
Okay, let me check 1 second.
Sorry.
Vera, could you share this, please?
Yes, I will share now.
Okay, thank you. Okay, so seems like it's coming up. So you can already start your pitch, Eneka. So you're very welcome to our meeting. So looking forward, to your insights.
That's I'm an advisor, so I'm not a manufacturing company. So that's just an overview or a very quick insight of two kind of co-package optics. So the next slide, please. Yeah. So CPO, why for? In fact, artificial intelligence demand is exponential. And so now data centers are facing two main challenges: lack of capacity and environment concerns. So that means CO2 generation, electrical power, and wafer consumptions. So nowadays technology are pluggable transceivers, and next will be CPO. So the estimated market is $4.5 billion. But the challenges remaining are the lack of standardization, so the interoperability possibility, and the large-scale manufacturability. Next, please. So just to put a figure in place, what China is doing, in fact, in this area. And we got some figures from Photonics 21 in 24. China has launched its National Integrated Circuit Industry Investment Fund, and it's a huge amount. It's 39 billion euros. So the competition, it means that, in fact, for China, these kind of technologies are really, really important. And so I've chosen to show you two CPO technologies from two European SMEs. One is from Israel, it's New Photonics, and the other one is from Switzerland, it's Enlitra. So New Photonics is replacing the ASP with PIC-based optical signal processors, while Enlitra has developed some COM laser optical interconnects for quantum computing. So next. So what is a New Photonics solution? So in fact, they have developed some PIC-based optical signal processor at 800 giga or even 1,600 giga. And so they have achieved some demonstration from 0 to 10 kilometers for data center, but as well up to 28 kilometers with Intel out of data center. And their main issue is still the photonics equalizer, because up to now they are limited to 200 giga. So their next challenge will be the stabilization, in fact. And regarding CPO, in fact, they have developed optical chiplet with a higher band rate, optical time domain modulator with a 50 gigahertz optical clock up to 200 gigahertz based on a single light source. And they have a high power efficiency and low latency. Next, please. Regarding Enlitra, they have developed a COM laser optical interconnects. And the advantage of a COM laser it's that all lines are coherent, because you have one single high power pump laser. And they have combined that with SEN micro resonator to produce some laser COM by a 4-wave mixing. And in fact, when you have more than 128 wave laser, you cannot no more use some classical laser technologies like DBR, for example. So you have to shift to COM lasers. So you have different type of COM lasers, mod-locked lasers, quantum dot, gain switch laser, or electro-optic COM. And Enlitra technology, so how I mentioned, they combine some one single high power pump with a micro resonator. And with this technology, they demonstrated high power performance in O-band at OFC 2024. And their main competitor is quantum dot technology. And so it's Candela in France. Next, please. So yes, I answer my own question. So co-packaged optics is clearly a game changer for hyperscale data center and artificial intelligence future challenges. That's my point of view. Thank you.
Okay, thank you very much, Annika. So great insights, some interesting messages you just shared with us. So please, raise your hands if you have a question for Annika. To address maybe the first part of your presentation. So what would be your advice to Europe? Having in mind all this international competition. Also the China's Integrated Photonics Growth Fund that you mentioned. So what should Europe do?
I would recommend. In fact, in Europe we have already some forces. We have the SHIP Act, for example, and we have one leader for this SHIP Act. It's Photon Delta, and in Netherlands, and around the Photon Delta in Netherlands, we have some other places in France, in Belgium, in Italy, in Switzerland, in Germany, of course, and I think we really need to maybe to gather, in fact, more efficiently our European ecosystem, because as the other before me, they mentioned PICs are a question of ecosystem building, and the most we integrate our own ecosystem, the more efficient we will be. And I think in Europe we have every single technical block, in fact, to be very successful, in fact. And well, just do it. and EPIC is one organization that is very efficient to do that. But maybe we need to be more active to the European Commission to get the funding, because you've seen the figures in China, and we really need to have the similar budget through the SHIP Act in Europe.
Okay. Yeah, I think I hear more and more of these opinions within our industry. So that's a good message, and maybe that's a good wrap-up message too. So if there is no further questions, so I suggest we thank Annika again, and let me just share a few quick wrap-up messages with you. So this was the EPIC Online Technology Meeting on Photonics for Hyperscale Datacenters for you. So this meeting was provided to you by EPIC, the European Photonic Industry Consortium, and also supported by PICs. I'd like to thank again all the speakers of today's session for making it such a memorable and fruitful discussion. So Chris, Javier, Anna, Wilfred, Ian, Chris, and Annika. Thanks again for sharing your views with us today. And I'm looking forward to continue these discussions with you at Photonics West and also at the upcoming EPIC activities, especially the one in FIX that will take place on the 24th and 25th of February in Enschede, Netherlands. So thank you very much, all of you today for your attention, and keep tuned with EPIC. You have now on your screen the poll to give us some feedback about this meeting, how you liked, what you didn't like. So please fill it in, and I see you on the next occasion. Thank you all. Have a good day.
Thank you.
Thank you, Ivan. Ciao.
Bye-bye.
Thank you. See you. Bye.
Goodbye.
Yeah,
Bye-bye.
goodbye, everyone. So the meeting room stays open for a couple of minutes in case you want to exchange some contact details or you have some last-minute ideas. So if not,